Hello and good day. So for today, we'll now discuss another supplementary lesson as a follow-up to our mathematical modeling for control systems. This time around, we'll be using Laplace transform as a way to be able to model electrical circuits. From the last video, we used differential equations and showed you the series of steps necessary in order to be able to represent the components, the currents, and the voltages into its appropriate differential equations. This time around, we will now be using Laplace transform, another discussion that you might have made during your differentials equations course. Okay? By using Laplace transform and try to compare it with the differential equations modeling, you will notice that doing this is much easier as opposed to using differential equations. So we will be using the same first example that we had from last time. For this specific video, I'll be only giving one example, as I already gave you one example during our lecture. You just have to remember our key things when doing Laplace transform. Hopefully, you still have a copy of your Laplace transform table, as that would come in handy when we convert voltages and voltage sources and current sources to its appropriate Laplace transform. Second, we must remember to be able to convert our passive components into its appropriate Laplace transform or impedance equivalent using Laplace transform, shown at the table above. So we have resistors. Resistors would not have any major changes with them. Inductors is just the impedance multiplied by S, which represents our frequency domain. And for capacitor, it would be 1 over S multiplied by the value of the capacitance. With that being said, given our circuit right here, you might be familiar, as I mentioned, that this has been given to our first example. Our first step is to convert our passive components and voltage or current sources into its appropriate Laplace transform. So for our voltage, which is V of t, you will be assuming that this is U of t, or a constant DC voltage for this specific purpose only. And from our Laplace transform, remember that so let us write here that this would be our step 1. Let me just erase this. So this would be our step 1, is to convert the appropriate components into its frequency domain using Laplace transform. So for the voltage source, for this one, we will be having a given that the voltage source is a DC voltage. So the Laplace of U of t. This is assuming that our voltage source is a DC source of U of t. Okay. So its Laplace will be 1 over S. Next, if we're going to convert the impedance for resistors, that shouldn't be a problem because it would be retained as is. So this 8 ohms and 10 ohms would still be the same. Now, the 1 Henry, as shown here, if we're going to transform it into its Laplace equivalent, we just have to get its impedance measurement, then multiplied it by S. So this one would become equal to S. Okay. S multiplied by 1, or simply S. Okay. Then our capacitor here at the middle, in order to get its impedance equivalent, we just follow the capacitor is equal to 1 over SC. Okay. So because the capacitor is 1 over 16, and this is 1 over SC, we just get the reciprocal of 1 over 16. So therefore, we will be getting, so let's write first. So this would be 1 over, so for the 1 here, then S, then the C is 1 over 16. So let's write it first here. Okay. So it would become, so we put this at the top, reciprocal. So our capacitance would now be therefore equal to 16 over S. Okay. So therefore, this would now be 16 over S, and this would now be equal to S. After converting the components into its frequency domain using Laplace transform, I would be redrawing the circuit, giving its new values for the frequency domain. So we have the 1 over S for the voltage source, and 16 over S for the capacitor, and S ohms for the impedance, or no, rather for the inductor. The resistances were not changed, so there's still 8 ohms and 10 ohms respectively. After we have finished the first step, our next step is to get the loops using KVL, as we will also be using mesh analysis, just like what we did with the differential equations. So we'll start with loop 1, then loop 2, and we will be representing the voltages as the product of the current passing through it and its impedance. So let us begin with our first loop. Okay, so let's move this a bit. So we have our loop 1. Oops, let's change this to black. So this would be our step 2 already. So we start with our first loop, or loop 1, which represents our I sub 1. So as always, the voltage sources are on the left side. The one that draws the current or uses the voltages or are on the right side. So we have our 1 over S, our voltage source, equal to the voltage here in our 8 ohms. So that would be 8 ohms multiplied by I1 plus, just like what we did last time, I1 and I2 are passing through the capacitor. So this would be 16 over S multiplied by I1 minus I2. Okay. Generally speaking, this is already our loop. But one of the things that we use to simplify the derivations or computations using Laplace transform is we want to make sure that we don't have a denominator of S on our terms. So what we do, we multiply the whole equation with the highest order of S. In this case, we only have S in the denominator, so we just multiply every term by S. So if for some reason there is an S squared at the bottom, so we multiply every term with S squared, and etc. Now, if there is a scenario that there is no s in the denominator, so we don't have to multiply it with s. But I haven't encountered a problem like that yet. So we multiply everything with s. Again, this is for simplification purposes. That would make our further computations easier in the long run. So again, we multiply by s as we want to remove s in the denominator. So when we multiply this, this would become equal to 1. This becomes 8 I1s. This one cancels out. So this would become 16 I1 minus I2. Don't forget the parentheses. Now you might be asking, would it be all right to actually distribute the 16 already, or multiply the 16 with I1 and I2? Well, that is something that you could do already, as in one of the computations rather. We would actually do that. So let's go ahead and distribute 16 already. So 1, 8 I1s plus 16 I1 minus 16 I2. So after distributing 16 to I1 and then to I2, you'll notice that we have two terms that have I1, and then we factor out I1 from both of them. So we will now have 1 is equal to 8s plus 16 multiplied by I1 minus 16 I2. So this would be the final form of our loop for our loop number 1. So as you can see, there are no s in the denominator, and I1 and I2 are grouped together already and has been factored out. Let's do the same with loop 2. As there are no voltage sources, our left-hand side would be 0. Start with the middle. So 16 over s multiplied by I2 minus I1. If you watch our video from last time, you would know the reason why I had I2 minus I1 in loop 2 and I1 minus I2 in loop 1. So go ahead and refer to that. Then let's go to our inductor, which is S. So that would be SI2. And then we have 10I2 for our resistor. Okay. Now, just like what we did with loop 1, we have an S on the denominator. So we have to multiply everything by S. Like that. So this is not 5, huh? This is S, so this would be 0. S would get cancelled out here, so we have 16 multiplied by I2 minus I1. S times SI2 would be S squared I2. And finally, we have S times 10, so that would be 10S I2. Let's start distributing 16 for I2 and I1, just like what we did with the previous equation, or previous loop. So this one would become 16 I2 minus 16 I1 plus s squared I2 plus 10s I2. Now you would be able to see that we have several instances of I2 in 3 terms and only one with I1. So let's go ahead and factor that out. So we have the negative 16 I1 here. Put it on the first term as the first term, so to be consistent with our loop number 1. Okay. Then we are able to factor out I2 on the other side. And we'll start with s squared because we have s squared, 10s, and 16. And normally with quadratic equations or with polynomials, we write it in decreasing exponent form. So we start with s squared. Okay. I won't write I2 because I2 is the one that we're going to factor out. Then we have 10s. And then we have 16. And that would be the time that we will be factoring out I2. So this would now be our second equation, which represents loop number 2. Afterwards, we will now be able to represent our current I1 and I2 using either substitution or elimination. So we used elimination from last time. So this time around, we'll be using substitution. So we'll get I1 from one of these values here. Okay. And then we will substitute it on the left-hand side. Or we could use I2 and then substitute it on the other side. And that would be our next step. Now let's move on to our third step, in which we would now be able to get the frequency domain equations for both I1 and I2. As mentioned a while ago, we could use any method that you have learned in your linear algebra class in order to eliminate one equation from 2 equations to unknowns. So in this specific scenario, we would be using substitution as our method in trying to eliminate one of the variables and get the value for either I1 or I2. Now, it really doesn't matter which loop you use or which current or variable you want to retain or eliminate. As from my experience, if you tried looking for a loop with a variable that is easy to substitute, the hard part actually comes in once you do the reverse operation and vice versa. In any case, let's arbitrarily start with loop 1 as our choice for the equation, and let's use I1 as our variable of choice. So we have here 1 equal to 8s plus 16 I1 minus 16 I2. Okay. Let's move this a bit at the top. So we want to leave I1, so I'll have to transpose 16 I2 on the other side. So this one here. Let's move it on the other side with 1. So this would now become 1 plus 16I2 equal to 8s plus 16. Okay, so I have the variable I2 on the other side. We just want to leave I1. So we divide both sides by 8s plus 16 in order to cancel out the 8s plus 16 coefficient of I1. And then I'll flip it. So I'll have I1 here. Would now be equal to 1 plus 16 I2 multiplied by 8s plus 16. Okay. So technically these are actually two terms, 1 over 8s plus 16 and 16I2 over 8s plus 16, which you could actually further simplify if you want. Okay. So this, we could use this, well, depending on the situation, or you could have it like this, 1 over 8s plus 16 plus 16I2 over 8s plus 16. 8 is a common factor for this one, so we divide, factor out 8. So we have 1 over 8s plus 16. So we divide 16 by 8, 8 by 8, and 16 by 8. You just factor out 8 and would cancel that out. This would become 8 times 2, and this would become 8 times s plus 2. And then it would cancel out. So this would become 2I2 over s plus 2. There we go. Hopefully you still understood how from this part we're able to get this part. Again, 8 is a common factor for the numerator and denominator. And cancel that out, and you get 2. When you divide this by 8, you get 2. You get s only, and then 16 divided by 8, you get 2. So you can either use this or this, depending on the situation. Okay. We have this one or this one. Now, once we are able to isolate I1, we can actually use this and then replace it in the second equation. Sorry about that. In our loop 2. So let's write that down again. So we have 0. Oops, let's use the black ink. So we have 0, negative 16 I1 plus s squared plus 10s plus 16 I2. And because we already have I1 here, we just replace it with this one. Remember, this is negative, so we'll substitute I1 with this. Let me just leave a space for the solution. So we're going to substitute that here. Okay, remember that this is negative. Okay. So that would be 0. Then we have the negative 16. And then we'll replace I1 with this equation or that equation. Looking at this, I think I'd prefer using this instead. Okay, you'll see later because I'll have to remove the denominator anyways. So I might just have to use this so that they are in the same equation. So 1 plus 16. So I'm not gonna use this. Let me just erase this. Instead, I'll be using this. So 1 plus 16 I2 divided by 8s plus 16. There you go. Then we have the plus s squared plus 10s plus 16 quantity I2. So only I2 is remaining. We just have to isolate I2 by using algebra as a means. Do it. I'll just have to multiply each side first by negative 16. So this would become negative 16 minus 16 squared would become 16 squared. That would become around, let me go ahead and check that. Just a moment. Where's my calculator? 16 x. Yeah, 256. So this would be minus 256 I2 all over 8s plus 16 plus s squared plus 10s plus 16 quantity I2. Okay. Then we have to eliminate the denominator. The reason why I use this is because I use this, I'll have two denominators to eliminate instead of only one. So I multiply the whole equation by 8s plus 16. So multiply it by 8s plus 16. That would cancel this out. I have to multiply and distribute it to this part. So I'll be left with minus 16 minus 256 I2 then we have we can have to distribute this 8s times s squared. I'll also put I2 in there as well. 8s s squared and I2, so that would be 8s cubed I2 then we have 8s plus 10s, that would be 80s squared. 8s times 16, that would be 128 I2. Just rearrange. 128 I2. There we go. Then we'll multiply 16. 16 plus times s squared. So 16 times s squared would be 16s squared. Oh, there should be an s here. 16s squared. 16 times 10s, that would be 160s. 16 times 16, that would be 256. I forgot to put the I2, because I need to distribute this, so we can go on with the next step. Let me just recheck. 8s s squared is 8s cubed. 8s 80s squared. 8s 16 is 128s I2. Get I2 here. So 16 and s squared, 16s squared I2, 160s I2, and 256 I2. So we'll combine the We'll now combine the same order of variable. So we start with s cubed, so we only have s cubed here. So we have 8s cubed I2, and then for s squared, we have 80s squared and 16s squared. So that would be 96. 96 s squared I2. Then we have S 128 and 160. So that would be 288 SI2. So 8s cube I2 plus 96s squared I2 plus 288 SI2. So 128 plus 160. Good. And then we have now minus 256 and plus 256. This would get eliminated or cancelled out. And we have this negative 16. Just move it on the other side, as this doesn't have any variables with it. Transpose. So this would become actually positive 16. Well, we're still going to factor out I2. So 16, 8s cubed I2 plus 96 s squared I2 plus 288. Wait, I was going to eliminate, factor out I2. I forgot. So 8s cubed plus 96s squared plus 288 s I2. Okay. And then we just divide both sides by this. Now we have I2 equal to 16, and then 8s cubed plus 96 s squared plus 288s. There we go. Okay. Let me go ahead and check this out and verify. So negative 16, the negative 16 here came from this one, from that one as well. Okay. Just point out my mistake anyways. Let's try simplifying this a bit by factoring out divisible by 8 is 288 divisible by 8. Yep, divisible by 8. Yes, so all of these are actually divisible by 8. So we can factor out 8 on all of them. So we have 16 8s s squared plus 96 divided by 8 would be 12. So 12s, and then 288 divided by 8 would be 36. We'll be able to simplify this, and then finally we have I2 would be 2 over s multiplied by s squared plus 12s plus 36. And this would be our I2. Now once we get I2, we can now use this and substitute it either here or here to get I1. So where do you want to put that? Let's just use this. I use this. Well, let's just use this. So we'll have the equation again, which is I1. I1 is equal to 1 plus 16 I2. But instead of using I2, we're using the big bad equation here. So 16 8s s squared plus 12s plus 36 divided by oh no, I made a mistake here. Just a moment. Seems that it'll be easier to use this instead. Let me just go ahead and say we'll just use the other one. Oh, what the hell, we've already started with this one, so might as well use this instead. We just write this. So what's that again? So 16 8s s squared plus 12s plus 36 and then at the bottom we have 8s plus 16. So we multiply this and we separate them out. It's like something like this, technically. So we have 1, 8s plus 16. Then we multiply this. Oops, not equal sign, but a plus sign. So I'm going to separate this one here and this one. So this will become 256. 8s s squared plus 12s wait, why is it this 8s? It's only s2. I'm using the wrong equation. Should have been 2. I already eliminated that. I forgot. Let's fix that. So this is supposed to be 2, and this is 2. 36. There you go. Then divided by 8s plus 16. Then we put this at the top side. Oh. Then we'll put this on the top side, reciprocal. So we will be having 1 over 8s plus 16 plus 8s plus 16. We put it on the top. So 2 8s plus 16 divided by s squared plus 12s plus 36. Okay. Now you can have this distributed, then we can have them expanded. Let's try doing that. So 1, this is still 1 over 8s plus 16. Then we have the 2 here. 2 times 8s is 16s. And then s squared plus 12s plus 36. Then 2 times 16 is 32. Multiplied by s squared plus 12s plus 36. Now, you'll notice that we can actually have this cancelled out, which is true. And for one final time, we will be having I1 is equal to 1 over 8s plus 16 plus 16 over s squared 12s plus 36 plus 32 s squared plus 12s plus 36. Okay. So I told you a while ago that it would be easier to start but complicated at the end. Or if we tried using I2, it would be hard at the end, at the start, but it will be easier at the end. So regardless of what you choose, it's technically the same. So this will be our I1. Hopefully I didn't make a mistake. Just go ahead and check and see if I did everything correctly, especially algebra. I tend to get careless from time to time. And I'll just have to redo the video instead. So tell me otherwise. And we already have our I1 and I2 here. Okay. And this would be our mathematical models for I1 and I2. Now, what if we're going to use the I1 and I2 here, and we were asked to find the voltages for the component. Let's say we're asked to determine the model for the voltage running here at our inductor, which is S. So it's just as easy as multiplying S by the current running through it, which is I2. So our V in the inductor would be something like this. So it would just be the voltage on the inductor. Just put an I here for the inductor. Would be equal to Z, the inductor. Just put L here instead. Multiplied by the current running through it, which is I2. So we just have to substitute. Let's say our ZL is already S, and we just multiply it with our I2, which is 2 over S squared plus 12s plus 36. So we just write down here. So it would be 2 S multiplied by S squared 12 S 36. S squared 12S plus 36. Then we can cancel this out. So our VL, or the inductor, would be 2 multiplied by S squared plus 12. So you can do it in every component as long as you already able to get the current for all of the loops, I1 and I2. The only thing that would be hard here would be the mathematical model for the voltage running in 16 over S, as this would be I1 minus I2. So that would be 16 over S, which is our Z, multiplied by I1 minus I2. And this is our I1 subtracted by this one, our I2. So technically, well, we can use this instead. Technically, this is already our I2 as well. So what would happen is this: we subtract this with this, and they have the same denominator. So something would change here; it would become 30. This would still be 16. So more or less, well, you can put it here, and that would just be 30, and then multiplied by curve or the inductance. Okay? So hopefully you were able to understand our series of steps involving the mathematical modeling using Laplace transform. Well, if you were able to go through with the differential equations, this would be a bit easier, as we won't be doing derivatives or integrals, but instead we'll just be relying on algebra. If you find any mistakes with what I did, kindly put it on the comment section below or message me so that I can fix my mistakes. Anyway, thank you very much for listening and have a great day.